This conference will now be recorded.
Okay, this is the video for some extra examples from the section 3.3 and 3.7. Starting with this one, discuss the concavity of this polynomial and find its points of inflection. I've already included the graph over here so you can already kind of see the points of inflection, but we want to prove that. So we need to find the second derivative. So let's take the first derivative. So this would be 4x cubed plus 3x squared minus 6x. And then the second derivative would be 12x squared plus 6x minus 6. And that one we're going to set equal to 0 and factor. You can divide a 6 out of everything. So that would be 2x squared plus x minus 1. If you try factor by grouping, the only way that's going to factor is with a 1 and a 2, where the 1 is negative. So that would be plus 2x minus x minus 1. And if we factor by grouping, that is 2x and then an x plus 1 minus 1, x plus 1. So we get x plus 1 and 2x minus 1, which means for our possible points of inflection, we're looking at -1 and 1/2. So remember, our next step is to put them on a number line from least to greatest. -1, 1/2. Both of them are defined in the original function since this is a polynomial, so they are possible points of inflection. The test for sure is to plug the test values we're going to pick into the second derivative and see if it comes out positive or negative. To be a point of inflection, your value has to be defined in the original function, and it has to have a change of concave up to concave down or concave down to concave up. So if we pick a test value of -2 and then 0 and let's say +1. So we plug those into our second derivative, which is right here. That would be 12 times 4, because it's -2 squared, plus 6 times -2 minus 6. So that's going to be 48 minus 12 minus 6. That's going to come out overall positive, which means this region is concaved up. If we put in 0 into the second derivative, that's just going to come out as -6. So that's negative. So that means this region is concaved down. And if we plug in +1, that's 12 times 1 plus 6 times 1 minus 6. That's going to be 12, so that's positive. So it goes back to being concave up. So as long as you have a flip-flop between each one, then that means they're both points of inflection. So to find your actual ordered pair, remember you put the value into the original function. So that is going to be 1 minus 1, so that's 0. That's going to be -3 plus 1, so that's -2. And if you notice, that makes sense because there's that point. And so we know that -1, -2, oh, that's not writing correctly, is an inflection point. And then if we plug in 1/2, that's 1/2 to the 4th plus 1/2 to the 3rd minus 3 times 1/2 squared plus 1. If you type that all into your calculator, you get 7/16. So that is the point 1/2 7/16. That is also a point of inflection. And you can see those are exactly what we would get on the picture of the graph as well. Okay, so we're going to move on. Essentially, I did skip some stuff in class telling you that it's not actually on the test or on the homework. I might do a video later on once we're not so worried about, what's going on for the test to show you these two problems because they're really interesting, especially if you do ever want to go through and do more math. They're important to see. So I'll put that on a future video. But we had at least one more polynomial that I wanted to cover in these curve sketching problems. Excuse me. So this one was given to us, and it was also pre-factored since this one does not factor nicely with using
This conference will now be recorded.
Okay, I was having some audio issues, obviously. So we're doing this curve sketching, and this function was pre-factored for us because you have to use the P over Q method, or the C over D, depending on which way you learn it. The rational root theorem is the only way to factor this one. So since it would have been too hard to factor that, it's been pre-provided for you here. So we're going to look at how you find the x-intercepts. Well, remember, you set the function equal to 0. So since it's already pre-factored for us, the x-intercepts are easy to see. It's going to be -5 and +1. So -5, 0 and 1, 0. If you want the y-intercept, you should plug back into the pre-factored version, because that's just 0, 0, 0, and then it would be 5. So that means the y-intercept is 5. So then we want to talk about, do we have relative maximums or minimums, which means we need to take derivatives to figure that out. So we're going to take the first derivative, and I would not use this version because you have to use the product rule to do that. We can just use the original polynomial. So that would be 3x squared plus 6x minus 9. Set that equal to 0. I can pull a 3 out. And let's see if we can factor that. Would that be, that'd be a 3, and then that's x plus 3x minus 1. So our possible max or mins happen at either -3 or +1. So we'll want to do the first derivative to check for increasing or decreasing around each of those points. So -3 is smaller, 1 is larger. We can pick -4, 0, and 2. Plug those into the first derivative, which is y prime in this case. So if we plug -4 in, that would be 3 times -4 squared plus 6 times -4 minus 9. That's 16 times 3, so that's 48 minus 24 minus 9. That's going to come out as an overall positive, which means we are increasing on that region. If you plug in 0, you're just going to get -9, because that's easy to see. The x's are going to go away, so that means that region is decreasing. And if we plug in 2, it's going to come out positive. I'm not going to write it all in, but you can use your calculator, plug it back into the first derivative, and notice that it comes out positive, which means we are increasing on that region. Okay, so what that tells me is increasing and then decreasing means we had a max, and decreasing to increasing means we had a minimum. So to find the actual values, you have to go back to the original function. It might be easier to plug into the factored version here. So -3 plus 5 and -3 minus 1 squared, that is +2, and that'll be -4 squared, so that's 16. So that's going to be 32. So, and that was for the relative max. So our relative max happens at -3, 32. To find the minimum, we want to plug +1 into the function, which comes out as a 0 for this guy. So it's our, which you should have already seen. We already had this point before, so it's going to be that x-intercept. To find points of inflection, we need to take a second derivative, and that would be 6x plus 6 using this. If we set that equal to 0 and pull a 6 out, looks like that's going to be a possible point of inflection at -1. We have to test it to be sure. So I'm going to plug in 0 will be on the other side. And I'm going to plug in -2, and we plug it into our y double prime. I keep wanting to call it f. So if we plug in -2 to this, that's -12 plus 6, that comes out negative. If we plug in 0, we get a positive. That means I'm concave down on this region, concave up on this region, which means that is a point of inflection. So go back to the original function, and I'm using the factored form. -1 plus 5, and then -1 minus 1 squared. That's going to be a 4. That's -2 squared, so that's 4. So that's going to be 16. So -1, 16 is the point of inflection. And remember, you cannot have asymptotes if you have a polynomial. That's only if you have x in your denominator. So we're going to take all this information and we're going to sketch the rough sketch of this using the calculus information. So I'm going to have to probably count by something like 8, just because how high these get. So I'm going to mark that this is 8, 16, 24, 32, And I'm going to count by probably 2's on the bottom. So 2, 4, 6, 8, 10, -2, -4, -6, -8, -10. And then this will be 8, -8. So you need to be consistent on your y-axis. And you need to be consistent on your x-axis. They can be different from each other, but you need to be consistent on top and bottom and right and left to each other. Okay, so -5, 0 will be, this is -4, so it's going to be halfway between that and -6. 1, 0 will be halfway between 0 and 2. -3 is here, and then down, or excuse me, up 32, so that's there. Let's see, 0, 5, that's going to be a little over halfway on the y-axis. So I'm just going across. I've already got that point. And -1, 16. Okay, so what we know is from -infinity to -3, we are increasing, and concave, and up to the -1, we're going to be concave down. So increasing and concaved down. And then we are from -3 to +1, which is part of this. We are still decreasing. So that's to that. And then we start increasing forever. And that matches that from -1 to forever, we are concaved up. So there's the sketch of our graph. So this is using calculus instead of using the methods we would have taught only in 136, which were kind of, they got us a general sketch, but they never really got us those maxes and mins and where did the bowl flip. So like I said, the one on the test is a calculus based version that you have to do, and it's a polynomial. So on the homework, I got special permission since we were about a half day behind. There was one like this on the homework, and I believe like this. Both of those you can skip. I told you that in class. I will give you the credit for those after the homework has lapsed. So mainly I just want you focused on polynomials because that's the type that we're going to have on the exam. And I will do, like I said, there's a couple problems that we said aren't on this exam, but I still feel like they're useful. After we get done with the test, I will do a video over those extension problems so that if you really are interested and you want to see how to do the more advanced stuff, that you can still watch that. All right, I'll see you guys this week.